Perfect. So great. Welcome everybody to this talk. Right, it's a great pleasure to have Boris Bukh. Actually, he's local for this semester, so he's in TH. You even see him giving a talk on the board, which is good and quite unusual for our seminar. Most of the time, speakers are from far away. I also want to mention that Boris is giving a really exciting course on discrete geometry in our FIM Institute. Actually, he's speaking in exactly the same room where he's giving the talk. And no, not the same. Okay, but but anyway, in the same building. What is important that the Boris's course is recorded. If you're interested, you can go to the FIM website and see the topics of the course and also the recording. Okay. But today the topic of the talk is not geometry, but actually additive combinatorics. And so Boris will talk about additive basis, change of domain. Please, Boris.
Thanks, Benny. Thanks for
maybe one remark, Boris. Keep the talk at 55 minutes. Sorry.
Don't worry. Okay, thank you. Okay. One thing you should know, I discovered in ETH here, you don't have clocks in the room. So let's say if I run over time, it's your fault. Okay. And I do want to say to the audience, again, please feel free to ask questions, during the talk. People in the room, of course, it's easier. For people who are remote, just unmute yourself, say whatever you have to say, and just mute to avoid the feedback loop. Okay, so and I can see some of your screens on my screen, so if you want to turn your video on, I might be able to actually see you as well. But again, so okay, and of course I can see people in here. Okay, in high definition. All right, so let's start with the math talk. So I'll be talking about a joint work with, first of all, with two Peters, Peter Keevash and Peter von Hintum. And the topic is additive basis. So additive basis is it's a concept basically which originates basically from Boring's problem. So basically, Boring long ago asked about writing every natural number as a sum of some bounded number of k powers. So, for example, he was motivated by Lagrange's theorem, which says that every natural number is a sum of 4 squares. And I know he basically wondered whether the same similar thing holds for cubes, 4 powers, and so forth. And again, the question was, Boring's question was resolved eventually by Hilbert in a beautiful argument, which nobody knows these days because it's been superseded by the circle method. But the Hilbert's argument was actually very different, and it's really cool. Anyways, and there's like a huge story about that, but I'm not telling you about the story about Boring's problem, or even related questions about which kind of people came up later. For example, so now basically what people mean by an additive basis is a sumset, so like say k powers, so that every element of n can be written as some number of elements from this set. But we will look at slightly more general concept. So let me define that. We say a set B is an additive basis of order k for A if every element of A can be written as a sum of k elements from B. So in symbols, what they're saying, A is contained in a set of all Sounds like that. Okay, and so this this thing here, I will conventionally we will just write it as this sum, or for simplicity, it's just k. Yeah. So that's this is okay. K false sumset. We mostly will focus on the case k equals to 2. So this is, and in this case, I meet the qualifier order 2. I will just say it's a basis for A. So in this kind of more general context, the problem was looked at various settings. For example, at some point, say Woolley asked, about finding a basis for things squares and kth powers, and those questions are. I mean, there's some progress, but basically they are open, like to prove because it's kind of really hard to prove. It's hard to find a basis for this kind of specific sequences. Okay. So what are we talking today about? Well, we are talking about the following quantity, which I will denote L of A. Okay, I'll leave some space here in case you're taking notes. Do leave some space in your notes as well. So this is the minimum size of a basis B for the set A. So A is contained in B plus B. Okay, and again, I will leave a bit of space here as well. Okay, so that's kind of the most efficient way of representing A's. As a kind of example, again, another kind of basically go back to basically like where the kind of question started. The another kind of instance where you can think where this occurs is, for example, let's just basically just to make sure we are kind of on the same page. Let's look at say L of the numbers one friend. So basically, I want to basically cover all the numbers one friend by sumset. So I would write, okay, how large do I need to make B? Okay, and this is a question to the audience. So somebody will have to unmute themselves and say an answer. Anybody can give me a lower upper bound construction, anything.
It's at least square root n.
It's at least square root n.
Because you only have B squared sums.
Yes, exactly. But with Pigeonhole principle, because actually you can even prove it. It's actually at least you can get square root of 2 there, because it's like if this is has size m, there m choose 2 sums. Okay, so it's square. And you can actually make it about size by square root n. For example, you can take multiples of square root n and all the numbers from 1 to square root n, and that will be. And again, you can actually get very close to this bound. And these things are called additive, thin basis, and there's going to have quite a bit of subject about that. But again, this is just to make sure people understand what we're talking about. Good. Now, but what we're going to do is we're going to here implicitly we were we're saying okay, we can take B to be numbers, say natural numbers or so forth. But really, it's maybe, and sometimes it is the case, it's actually better to take, say, maybe B, which are maybe rational numbers. Maybe, fine, my set A is a set of natural numbers, but maybe if I use B's to be rational numbers, maybe I can do better because I have more freedom. Yeah? So this is exactly the kind of question that we're going to study. So I will now fill in these blanks which I've warned you about. So D will stand for domain. So this is the domain where B lives. And so this is basically, and so here are two questions. So these are questions of Rouge. So put Imre Rouge, which he asked last year, last year at a conference in Budapest, and it's kind of got me and Peter's thinking. So the questions were the following. The first of all, how much larger can the L of N A be than then C. Okay, this is question 1. And the question 2, how much larger can L of Z be than L Q. Okay, so let me explain what it means. So in both of these questions, we are assuming that A is actually in the appropriate domain. So here we're asking like, what's the most efficient way to cover A by a sum of two sets of some set of natural numbers, and similarly here for this some set of integers. So this in the question 1, this is for. We are assuming implicitly that A is some subset of the natural numbers, because otherwise, of course, we cannot cover, find the many bases of natural numbers. And similarly, in question 2, we are implicitly assuming that this is some set of integers. Okay. Question 2 is slightly easier, so I will start with that. And just to get you kind of idea and simplest example that actually there is some difference between the two. Let's just simplest example is take my A to be just a singleton consisting of just 1, for example. Yeah. Clearly I can if I'm using rational numbers. Well, that's easy. I can take my B to be just a singleton 1/2. However, if I'm restricted to using only the integers, I'm stuck because I cannot. One element is not enough. The sum of an element with itself will be even, and this is an odd number. Okay, so we need at least 2 elements, and of course 2 will be enough. So that's an example of showing that these two things are different. The question is, how different are they? So let me tell you the answer. Well, I would say the answers can maybe. Okay, please let me know about visibility. So Benny told me earlier that this board, in this position, I think should be visible. But please let me know if people have difficulty seeing. I'm assuming that online people cannot, probably can still see this board.
So Boris, this board is also visible as long as people don't put it in full screen, but just make it bigger. Full screen somehow eats part of the screen. So my suggestion, that's what I did.
Okay. Okay, and I can always pull things down if people have questions. So, okay. Good. So what's the answer? Well, the answer for this question 2 is basically this example is as bad as it gets. The difference could be double, but not worse than that. Okay. So here is for theorem 1 is the easy theorem, and then so if some set can be covered by a B plus B, where B has size n, then it can also be covered by 2n. So this is the easy result. And again, we will see proof in just a minute. And the second result is actually the one which is more interesting, and we'll also see the proof of that, but this will be slightly longer, and showing that this is sharp. So it's a construction. So the interesting part is the construction. So there exists an A, and again, A for any n you like, for any n, such that size, and you do need basically double.
The letter should be LQA.
Thank you. Thank you. Okay. So let me tell you proof of this. It's really simple. So let's take a B. Let's take B, which such that B plus B contains a B is some set of rational numbers, and B is to have size n. B has size n. So I will now we'll make a new set of integers which just consist of all the elements which are just the elements of B rounded down and the elements of B rounded up. So this is a set of twice the size. And I claim that this actually covers it. And it's a simple argument because what you do, you start with an A, you write it as say bi plus bj for some I and j. Okay, so and then what you do, you just look at the following numbers. One is the rounded down version of the bi bj. The other one is the rounded down, rounded up, and then both of them are rounded up. Okay. Yes. Okay. Actually, I don't. So clearly, this number is smaller than or equal than A. Okay. This next number is bigger or equal than the preceding one. This one is bigger than the preceding than this one, and this is bigger than, this is strictly bigger than A. So this is, this is strictly, small, this number is strictly smaller than A. This is strictly bigger than A. And each time we change by 1, so at some point, we're actually going to hit the exact number. Okay. So this, okay, so let me just, I probably should not, write it slightly differently, but points we have 3 numbers, this, and this, differences at most 1, and we go from being below A to above A. Okay, so that's the proof.
The first number is not strictly smaller than A, maybe big integers, right? So it's exactly, yeah. Okay.
Sorry, thank you, yes, thank you, Benny, for keeping me honest. All right, okay, this the construction is more fun. So the idea for the construction, and this is also, we'll see also the same later, is to essentially make the elements of A basically variables, and just show that so if there is elements of B essentially variables, and essentially that means we will be able to introduce it to the essentially some problem in linear algebra. So let's see how that works. And actually, because we cannot solve this linear algebra problem precisely, this is where we're suffering this square root n loss, and it's actually the open problem whether we can remove it. So we will see how it works. Okay, so proof of 2. doing fine, great. We are going to we're going to first select the set B of rational numbers. Okay, so how are we going to do it? So we are going to pick some B of in the integers, which is again will need to be picked in a few seconds, but again, just stay tuned. And we're going to let A to be B plus B. Then we're going to multiply all of these elements by 2, so we just double it. So this is why I wrote writing a dot. It's not a sumset, it's a doubling operation. And then they're going to add 1. Okay? So that okay. So this is to be announced, this is to be announced, and this is how our array is. Now, note that, and I'm going to choose my P to have size n. Know that this set is a sumset over in the rationals, and because we can think of it as follows, we can think of it as B plus a half, B plus a half plus 2 times B plus a half times 2 times B plus a half, right? So what we can do, we can think of it as in this way, right? Because we can just divide this one into halves. Okay, and so this way we see that this is this set by design has an additive basis of size n. And we and again we have the same.
Why you need to multiply it by 2? It looks like you could have do it with B.
Because because here, I mean, again, what happens if some elements of B are odd and some of them are even, then some of the sums will be odd, some of them are even. Whereas I want all elements of A to be odd to basically play the same trick I'm playing here.
Okay, I understand. Very good. Thank you.
You're welcome. Okay. Okay. So now let's play the trick which I just said we'll play. So now suppose that we have some way to cover A by some B prime plus B prime, and now B prime is set of integers. Now some of the elements of B prime are odd, some of them are even. So what I will do is I will write it as 2 times B0 union 2 times B1 plus 1. So these are even elements of B prime. These are odd elements of B prime. And the point is that the only way to cover an element of A is to take an element of B0 and add an element of B1. This is the only way we can do that. So from this observation alone, it's already trivial to get a lower bound, which is basically square root of 2 times n, because just because the number of elements covered is at most triangle size B0 and B1, but we can do better. We can actually get 2, as we'll see very shortly. Okay, so let me move the board.
Okay. Chris, maybe use 2 boards, because this is really not visible, the top one.
No, I don't expect you to see the third board. I just moved it out of the way.
Okay, just so that you know that the top board is really
I don't expect this is basically advertising for people to come in person, so they have better view. But yes, but I don't expect you to see the third board.
Okay.
So what we arrive at? We arrive at is that the B plus B is covered by B0 plus B1. Okay. And now the question is how to choose B so that the smallest size of B0 plus B1 has to be large in order for this to hold. And what we're going to do essentially choose this to be essentially generic elements, and this is going to work. Let me just explain what that means. Let me name elements of B. We'll call them Y1, Yn. And let me name the elements of the B0 B1. So say B0, this might be X1 through, let's say, XA. B1 maybe same thing but with the primes, so X1 prime up to XB prime. And now this relation here corresponds to the fact that we can cover with every element yi is of the form certain x, so certain, and this x will depend, of course, on I. So this is x, I'll call it f of I, and plus some x prime, again, let's call it gi. Okay? So we have so this is what this condition means, and this is for all I. For certain functions, f and g. So I will, these functions f and g, I'll call it a type. So it's a type of covering. So how we cover this particular B is in this particular manner, in this particular type. Okay?
Sorry, Boris.
Yes.
Can I ask you a question? I thought what you were writing is B plus B is inside B0 plus B1. Why do you say yi by itself is equal to some x plus some x prime?
So this is, I'm saying this condition, oh, sorry, you're right. Yi plus yj. Thank you.
Thank you.
Thank you. Thank you, Jigan. All right. So this pair of functions f and g records the combinatorial type of this covering. So now for each type, I can record what is the set of y's that works. I can cover in this using this type. So let's have say S, F, G. This is just basically a set of all the vectors y. So this is just vectors y1 through yn, such that the y prime is coverable by type FG. Okay, so, and this is the just an element of the Z to the N. Okay, now the key thing to note is that for at least one type, and this set is full dimensional. So the span of S, F, G is full dimensional. And the reason is really simple. If all of these sets were, each of them were contained in some hyperplane, then if you take union of all these hyperplanes, because there are only finitely many types, so like number depends on just n, it would be, it would not cover this whole space, and that's it. Proper set of finely manifold proper planes do not cover Z to the n, and it's a very easy exercise. So at least one of the sets is full dimensional. So that means that over if you now think of this as variables over the rationals, this system of equations has a solution with this particular type for any left-hand side, right? This is a solution. We can solve them over integers for some full dimensional set, but it means over rationals we can solve it for anything.
Sorry, can I still ask a question?
Again, of course.
So here a type is defined by x, x prime, and f and g, or only by f and g?
I'm not sure I understand the question. So type is this pair of functions f and g.
Yeah, so this set is only for y. Where is x? This definition S of fg, should x and x prime appear?
This is a curve. So I'm defining a type of a covering. So this is a type of this covering. So if the sumset B plus B can be covered by B0 plus B1 with this particular way, then there is a type recording how they're covered. So I have a function from sets B to types. Okay, and what I'm saying now, if this number LZ of A is less than something, then I'm just looking at all possible choices for B, right? For my Y's, and I'm claiming at least one of them I want to show this bound is for one of them. So now I'm recording all their types, and I'm saying, well, there is going to be a type. So let me just I should probably say.
Stefan was asking what quantifiers do you have on x and x prime, but I think the quantifier is there exists some x and x prime so that they cover y with the type fg.
It's coverable, yeah. So this is quantifier here. It exists access of this type. Sorry,
but then the key claim or something you said for at least one type fg. The point is that A and B are different from Y. Right. Okay. Yes. So you fixed A and B before, or?
So what I'm saying is, so maybe the way you think about it is the following. So if for every L Q for every A L Q A at most n, we have L Z of A is less than M, okay? Then for for at least one type with, to be precise, with A plus B less than or equal than M, this holds.
Okay, thank you. Yeah, that's what I want.
Yeah. This is the, I think, fully quantified version. It's just pigeonhole principle. Okay, let's see how good. Okay, so there is some kind of type which is full dimensional, and so that means this system, let's call it star, and so the star has a solution over rational numbers, right? Over Q for this type for all Y. So we've gone from knowing something about solutions over the integers, to now knowing solutions over the rationals. But what does it mean? So now we are going to apply this for y, which is one of the standard basis vectors. So E1, E2, and so forth up to En. So for each of these y's, there exists a solution to the system of equations of this particular type. What does that mean? If you think a little bit, that means that there exists vectors, a set of vectors, so C0 and C1. So these are now vectors in Q to the n, such that C0 plus C1 contains all the possible vectors of Hamming weight 2. So just sum of two standard basis vectors. And this is basically just follows by just think about what happens when this is just, so if the these vectors let me just write it up. It'll be simpler than explaining.
Do you assume this vector y is just a vector with n coordinates, so that the ith coordinate is yi?
So I'm using I'm using it basically for just the vector or for standard basis vectors, and I'm saying.
So are you applying yi n times or yi?
Yes, I'm using this n times, and I'm saying I'm getting n solutions. Out of this n solutions, I can make vectors. Let me just write it up. And this will be easier. And what I'm getting essentially a solution to a vector problem then. So, okay. So what I'm saying is the following. So take y1. So so what I want to be the So what we are essentially saying, if we can solve it for any percentage associates of scalars, we can also solve it for the set of vectors, where y1 is the first basis vector, y2 is the standard basis one, and we're going to get the x's and x primes are now the elements of Q to the n. And the way we do it is we are going to we are applying it where the y bar is just has just 1 in the first coordinate and 0 everywhere else. This will get us the first coordinates of x's and x primes, and similarly and so forth and so on. Because the system of equations here, we're just solving row just coordinate by coordinate using that effect. Okay. So what we have now is the following problem. And this problem we cannot solve fully. So this is how small can be, say, c plus 0 plus c plus 1 be if c plus 0 plus 3c equal 1 contains the sumset of the standard bases. And c0, c1 are just rational vectors. So this is a conjecture. It's that the c0 plus c1, it's got to have size at least 2n. And we believe this conjecture. Okay? But we can only prove the lower bound, which is square root n worth. Okay.
Sorry, how to get from this xi, x prime as vectors to c0 and c1?
Because this is so this is exactly the x. So xi's, this new vector xi is exactly set of c0, and xi prime is exactly the same. Because this is the same covering condition, except now we're covering not scalars, we're covering vectors.
Wait, I thought every xi is a vector, and you have n vectors. Right. Sorry. C0 is also a set of vectors. Okay, sorry, I forgot.
No. Thanks for asking questions.
It's like, so we have xi and I ranges from 1 through a kind of, and then there's x, maybe x prime j, where j ranges from 1.
Correct. Exactly. So let's now prove. So let's prove weaker bound. So for this, we're going to look at the smaller of the two. So say without loss, C0 is smaller of the two. And suppose it's got the size n minus something, n minus d. And let's look at the span of C0. So this is going to be a subspace of codimension at least d. Okay. It's going to be a solution to a system of at least d linear equations. So let's say d for, because the worst case is going to be if it's equality. So let's just say d for, just to make notation slightly easier. So it's a set of solutions to a system of equations which looks like this. So there's some x on blah blah blah. X2. So after putting it in a row echelon form, this is how it will look like. And again, I don't know what this is going to be, but it's going to be some kind of row echelon form system of equations. So by renaming the coordinates and just doing usual Gaussian animation, this is what we get. So this is our subspace. And so now let me define a subspace W. So this is going to be the span of the first d coordinates. Okay, and the key thing to note is that V and W are very disjoint. So even translates of them don't intersect much. So more precisely, if I look at the V plus any shift with W, this intersects at most one. So what does it say? Well, right, if shifting W by some vector means I'm specifying all coordinates except the force D, and I can do anything I want on the force D coordinates. So I'm intersecting with V. That means that all variables except the force D are fixed, and I need to solve for the force D. Well, there's at most unique solution to this system. Okay, so that's that. So what that means is the following. So now basically consider all the sums of the form EI, EJ, which are live in the side of space. So for the I and J is at most D. Now, each of them, so these are covered by C0 by C1. Well, but this is C0 is inside V, so this side V plus C1. But each translate of V covers at most one such sum, and that's it. So we need at least this many translates to cover all of the elements of this form. So if D is bigger than a proud square root, I mean, basically, but the argument which Alexa was talking about in the context of covering one frame, then we cannot do it. So the D. So if D is bigger than proud square root, then C1 is basically more than 2n, and since this is the smaller of the two, we are done. Okay. So this is and again, this result. Now, in the remaining 6 minutes, I believe, I want to tell you what happens for the other question of Ruja and some, and then without proofs at this point. And at that point, we'll stop. Okay, just recall what was the question. The question was basically, instead of comparing the Z with Q, we're now comparing Z and N. So here are the results. So again, the easy result is an upper bound. And it says that if LZ of A is N, then Ln of A, again, A is inside natural numbers. Is this now? It's going to be no longer linear. You might need to lose a log, so it's going to be n log n. And furthermore, this is part one. And furthermore, there exists A of any size you like, right, size n, such that LZ of A is n, and Ln of A is n log n. We unlike the previous results, we don't know what this constant here is. I mean, they're like factor of 30 apart in our proofs. And again, we can.
So you say A has size n and LZ of A is also n.
Sorry. Yeah. Of A for any n. For any n. any n such as this. No, of course not. Okay. So again, the construction is easy. It's some kind of fairly simple recursive construction for which I've had time. I will be able to explain very quickly. This is some kind of graph theoretical argument, which is kind of fun. There are also results. This also generalized partly to the higher basis, which again, let me just basically say in a few words. So what I showed you for the Z versus Q generalizes for basis order K, basically without huge changes. So again, it's a still factor of 2. And again, we are losing, instead of square root, instead we are going to lose n to its appropriate power depending on K. Okay, again, because we cannot solve this problem which I wrote here in full. This result, however, we do not know how to generalize to higher dimensions for a larger subset. We don't, for example, for basis for free, we don't know whether this needs to be nearly linear, so like n to power 1 plus epsilon, or it actually becomes significant superlinear, like n to power 1 plus epsilon, or maybe n squared. We don't know. One thing we can prove is that this does never becomes bigger than n cubed for any basis basis of any order. And again, the argument there is actually kind of fun. They found an approximation argument again, which is probably the hardest part of the paper. But again, this is definitely not something I can tell you about. And I think this is about my time. So I thank everybody for attention, both people in person and remote. Thank you.
Great, Boris. So thank you very much for the nice talk. So the floor is open for questions.
Okay, Alexa.
So one question is, here you look at, the field of rational numbers and their ring of integers, meaning the integers themselves. But then you can also look at any other number field and the corresponding ring of integers. Is it very easy?
This is not going to make a difference, I think, because really, if you take any torsion-free group, basic, I think it's going to be basically more the same, like Z versus Q, because basically, for example, if you replace Q by real numbers, nothing changes. It's the same answer. It's the same answer. But okay, now sorry, it took me a while to process your question. Now I understand your question. So what you can think of, maybe this because ring of integers, you're not using any multiplication here. So what you're really probably going to be asking is basically comparing n squared versus a z squared, or maybe some higher dimension, because you just take a basis. It's a good question. We don't know the answer to these kind of questions. One can show that again, it's going to be some constants, and so forth. In this, like going to be powers of logs in this case. For q's is going to be some factors. The interesting maybe version of that, which maybe we didn't ask, but maybe this is I want to mention, is look instead of addition multiplication. Okay, or z versus n. If you take basically like prime factorization, this would correspond to looking at that, and we don't know whether the it's going to be again n times polylog, or it's going to.
You mean multiplication in integers versus rational?
So yes, so basically, right. So this is basically if you just take a prime factorization, this is what you're going to get, and we don't know whether it's just some kind of polylog dependence here or it's polynomial. We don't know. No, maybe this is okay.
More questions? Okay, so maybe I'll have a question. So you said that the proof of 3-1, so maybe I misunderstood. I thought that the proof of the statement is some graph theory and the construction is recursive, right?
Yes.
And so in the proof of graph theory, so you build what, an auxiliary graph where the vertices are A.
So basically what you do, I mean, the basic idea is essentially similar to what I showed you. You want basically think of basically the elements as being indeterminants, right? So basically you want to take a generic set. And so essentially what you're going to do, you're going to select some kind of set x plus 1 plus 2. Like this is going to, you like a subset of that, this is a set of integers. And then your difficulty is covering elements of the form xa minus xb. And if you believe in this kind of transference to vector model, which actually does break down in this case, so actually when we had to write it, we actually could not actually use the vector transference in a clean way. But if you believe that it should hold, that again, when you're in your sets B, which you're using to cover, essentially you're going to have x minus xc plus something. This is kind of your vector, and you will be adding things like this to get this xa minus xb after this specific cancellation. And essentially, what you're doing, you basically draw an edge from A. You have basically from A to B, signifying this element, and you have some kind of element C. And now, basically, you have some kind of statement about directed graphs about like counting some kind of how many. It's kind of paths of length 2, but not quite. It's kind of object like this you're counting, and it's some kind of dyadic argument there. But again, we could not get a clean statement because again, transference was kind of breaking down partly. So if you look at the paper, it's actually not as clean.
Okay. Good. More questions? So if not, let's thank Boris again. Thank you, Boris. So next week we will have Tuan Tran, and I will send an announcement, and also it's already appeared on the homepage of the seminar. And again, thank you for coming. Hopefully to see you next week.